Sure thing.
So it's a pleasure to welcome Ben again for his second talk on Coulomb branches and cylindrical KLRW algebras.
All right. Well, thanks everybody for having me back. Everybody came back for a second helping. So I wanted to start. So this is sort of the same list of talks I had before. Of course, I added part one, and I added a link to a talk of Mina Aganagic about non-homology, which I'll mention a connection to later. You can find my slides on my webpage, so you can get the links from there. I know you can't click on them through Zoom. They should really they should introduce that feature, but I don't think they have it yet. So just to remind you what we did last time, the KLR algebras and generalizations of them, incorporating these red lines, can be gotten as convolution algebras for certain kinds of moduli quiver representations on a finite dimensional vector space. And then to get the Coulomb branch and that sort of related stuff, what you do is affinize. So everywhere that you had quiver representations with coefficients in C before, you now take quiver representations with coefficients in Laurent polynomials. So that's a perfectly good field. You can look at quiver representations over that field instead. And everywhere that you looked at flags, you instead look at lattices for the Taylor polynomials inside the Laurent polynomials. So you look at all the ways of choosing lattices in each space of the quiver representation that are compatible with the maps. All right. And the Coulomb branch is actually the convolution algebra you get when you look at sort of taking a quiver representation and taking two pairs of lattices inside it. And you know, just as with having a quiver representation over C and a choice of two flags, having these two lattices, that gives you a convolution multiplication structure on homology. And actually, in this case, it's commutative because of essentially factorization properties in the affine Grassmannians. So somehow you can think of this as something about having a disk and then doing something away from the origin in two different ways. And you can't actually do this with, you know, spec of Taylor series, but you should sort of imagine that you can puncture the disk at two places and then swap the two punctures. That's kind of morally what's going on here. It's the Ekman-Hilton argument. And another algebra, which will be, I'll sort of explain the relevance of a little bit later, but which just kind of naturally shows up if you're thinking by analogy with KLR algebras, is to say, wait, I shouldn't replace flags with lattices. I should replace flags with affine flags, which is, you know, as we discussed before, a chain of lattices. So you get this algebra that I'll call sans serif R. So I'm always using sans serif for affine things. All right. And these affinized algebras R have a very similar geometric presentation to the original KLR algebra. Somehow, locally, when you're just changing one or two steps, affine flags behave just like usual flags. And so you get the same local relations, but where the sort of affineness comes in is instead of drawing the pictures in a plane, you draw them on a cylinder, and you can get something interesting by going around the cylinder. That has to do with like taking a lattice and replacing it with a smaller lattice inside it. So somehow a surprising amount of this story is, well, you do all the stuff you did before, you use all the same local rules, but now you do it on a cylinder instead of in a plane. All right. Are there any questions about that sort of review of stuff from last time? Okay. That's good. So this is also reviewing from last time, but it was toward the end and I was going a little fast. So let me just say, why do I care about this construction? Why am I bothering you about this? Don't you have something better to do on your Friday afternoon? Well, the reason I like it is there are these very interesting examples of varieties that hopefully you like. The nil cone of GLN, symmetric powers of C2 mod a finite group, which of course many of you will connect with the Hilbert scheme of the resolution of C2 mod that group. And there's sort of a number of generalizations of these. I could say slow-to-be slices in type A, or generally type A quiver varieties and affine type A quiver varieties. So this is a very special case of affine type A quiver varieties. Now, all of these are quiver varieties, so I don't have to think about them as Coulomb branches to construct them in the first place, but I learn new things by thinking about them this way. That'll be sort of a theme of this talk. And I just want to remind you that, yes, they're quiver varieties, but they're quiver varieties for sort of different dimension vectors in different quivers. So there's this 3D mirror symmetry underlying this. So you would have to change the quiver to get these as quiver varieties. All right, so what's the advantage of thinking of them as Coulomb branches? Well, so one advantage that I'm going to try to get to at the end of this talk is that thinking of them as Coulomb branches gives you a new resolution of them. So these spaces all have famous resolutions: Springer resolution, the Hilbert scheme for symmetric powers. And BFN actually construct, using this Coulomb perspective, resolutions of all of these guys. Whenever you have an affine type A quiver gauge theory, that includes finite type A quiver gauge theories. And that includes all of these examples of special cases. And I'm basically going to be specializing to this case for the rest of the talk. I'll maybe mention when something really uses that and when something's true in general. So, of course, if you think of these as Nakajima quiver varieties, they have resolutions coming from Nakajima's construction using GIT theory. And that's actually a complete list of commutative resolutions of these varieties. So when I say new resolutions of singularities, I don't mean like what you would find if you open your algebraic geometry textbook and look up resolutions of singularities. I mean non-commutative resolutions. So if you have a symplectic singularity, you can talk about a non-commutative symplectic resolution. This is really the same thing as a non-commutative Crepin resolution, but for a symplectic singularity, being symplectic and being Crepin are equivalent. Sorry about that. So whenever I have a commutative ring, a non-commutative resolution is a non-commutative ring such that my original ring, A, is ERE for some idempotent. And whenever that happens, I have a quotient functor, which is take an R module and hit it with the idempotent. And that functor should homologically look like push forward by a Crepin resolution of singularities. So I'm not going to write out the whole definition. It involves things being Cohen-Macaulay and finite global dimension, yada, yada, yada. But the point is, being a smooth variety is kind of a homological property of the category of coherent sheaves. And you can, in purely homological terms, state what it means to sort of behave like push forward of coherent sheaves by a Crepin resolution of singularities. So this is sort of another way of taking a singular affine variety, so the spec of a ring, which is not such a nice ring, doesn't have finite global dimension, and turning it into something that behaves well homologically. All right, and it turns out when this BFN resolution exists, so in particular in the affine type A quiver gauge theory case, this ring R, which is this kind of generalization of the KLR algebra, but using cylinders, so whoops, this guy, is a non-commutative symplectic resolution of singularities. And its D equivalent, its category of modules, is equivalent to the derived category of coherent sheaves for any, whoops, I missed a tilde there, for any symplectic resolution of the Coulomb branch. I'll call it Coulomb branch. Math frac M without any tilde. So there's this sort of old idea from algebraic geometry of D equivalence equals K equivalence, that any two crepant resolutions of a singularity should have the same derived category up to equivalence. And this has actually been proven for symplectic singularities, and it's been proven exactly by constructing non-commutative resolutions and showing that all the commutative resolutions are equivalent to them. Yes, so Nitu asks, when I say Coulomb branch, what kind of field theory am I talking about? In this case, I'm talking about a 3D gauge theory with matter. That's n equals 4 supersymmetric. So it's not a basic question in some sense, but that's sort of the buzzwords to look for is 3D n equals 4 supersymmetric gauge theory with matter, if you want to clarify. All right, so this is the same context as BFN. How does the quiver fit into it? The quiver tells you what the gauge group is and what the matter is. So when I have this picture here, what this means is whenever I have a circle with an A in it, that means a copy of GLA in the gauge group. And whenever I have two nodes connected by an edge, that means HOM from CA to CB. Physicists would say a bifundamental. And whenever I have a circular node and a square guide, that means, and here I had B, that means I take CA and I take B copies of it. So it's the same representation and group that Nakajima uses to construct the Nakajima quiver variety, but you do something different with that group and representation. Or it's a bigger thing, right? There's this gauge theory. The quiver variety is the Higgs branch of the gauge theory, and we're interested in the Coulomb branch, and those are going to switch under 3D mirror symmetry. All right. Okay, cool. So this sort of KLR algebra story on a cylinder actually gives us a non-commutative resolution of singularities. And I'll just note here, in the cases that we like so much, the Nilcone and the Hilbert scheme, resolutions were already known. So this construction on the nose gives us what's called this non-commutative Springer resolution defined by Braverman-Finkelberg-Nakajima in type A, and more generally gives us a similar resolution of any parabolic slow to be sliced in type A. And for the Hilbert scheme, well, you have to do a slightly different construction that I didn't draw because the quiver for the Hilbert scheme has a loop. There's an extra C star of symmetry on the Nakajima quiver variety, and that has to get incorporated into the algebra. So you have to do this, what I call weighted KLR algebra, which I'm happy to explain, but it would just bog down the talk if I went into it. So if you look at the story I talked about with C star actions in the previous talk, you just apply that, incorporating some of the C star action with positive weight on the loop. But it's just an extra complication I didn't want to get into. But I will say there was no non-commutative resolution of the Hilbert scheme constructed, the symmetric power constructed by Braverman-Finkelberg and Ginzburg based on the Trednik algebra, and you recover that from this perspective. So you get back non-commutative resolutions you knew, and it sort of gives you an interesting whole family of them for all these affine type A Nakajima quiver varieties. Yep. Okay, so those guys are kind of my goal, to give you at least a little bit of a feel of why is that true, what interesting stuff is that telling us. Now, to sort of go down the road to get those resolutions, you have to do kind of an intermediate step first, which is you have to do a non-commutative deformation of these algebras. And this was kind of what I was getting to right at the end of my last talk. So I can think about everything in terms of the disk that's spec of Taylor polynomials. So in particular, I can think of, let me not actually try to write it out. Just remember these sans serif guys are the Taylor polynomial versions of things, and the Oifrak guys are the Laurent polynomial versions. So basically, by scaling my variable t, so maybe I'll actually write that. So I sort of act with C star and t. I said that here, good. So the parameter t has weight 1 under this action. So you'll often hear people talk about the loop rotation on these kind of varieties, and that just means let C star act by rotating the disk. So now I get a C star action on all these varieties, but I actually have some choices on how they act, because I can also incorporate a C star action on my original finite n over g. So here, my phi is a homomorphism from C star into automorphisms of this quotient stack n mod g. Or actually, maybe it's better to say into the normalizer in GLN of G. I know there's a lot of n's there, and that's mod G. So I just want to emphasize this phi. It's a homomorphism to the quotient. We talked previously about all the different ways of lifting that up to the normalizer, but now I just want the action in the quotient. All right. So that gives me a C star action on all of these guys, which is sort of weight 1 along the loop direction, and then has some choices in how it acts on the actual finite vector space. And so we can take that homology we considered before and make it equivariant. So we can include, the only thing that's changed here is I've included C star equivariance. And so now my homology has an extra parameter in it, which I'm going to denote h bar. And incorporating this C star equivariance breaks the commutativity, makes the algebra non-commutative, because my Ekman-Hilton argument had to do with taking 2 points on the disk and swapping them. I can't do that C star equivariant. So the C star equivariant algebras are actually non-commutative. And actually, if you're thinking about things diagrammatically, the change you have to make is very small. So all of the relations have sort of geometric explanations, and all you have to do is, when you calculate Euler classes, you have to remember how this new C star acts on things. So for example, this dot, that's the Euler class of a tautological line bundle. And when I go off the end of my cylinder and come around on the other side, I change how the C star acts. So I'm taking my affine flag here, and the way that the torus of the group acts on successive quotients is periodic, but as I go down my affine flag, because I have to multiply by t to get between things that differ by m, I'm going to change the weight of things. And this appearance of this term with an h bar is exactly telling me how that weight changes. And the other thing I have to be careful about is here. So I had to choose that phi. In my quiver case, this phi is really going to be a map from C star to the product of the GLs of the WIs. So it's assigning a weight to every basis vector in C to the WI. And each one of those basis vectors is a corresponding red strand. So it's assigning a weight to every red strand, and I have to deform the relation of cross that red strand and come back by adding in a term that depends on that weight. So in all of these cases, I look at the calculations I did before in algebraic topology, and I pay attention to how that C star is acting. So it's sort of very simple deformation, but that exactly means that I switch from functions on the nil cone to the universal enveloping algebra of SLN, and from functions on some parabolic Sloterdijk slice to a W algebra, and from functions on that symmetric power to a spherical Cherednik algebra. So even though this is a very simple change, it gets you much more interesting algebras, well, interesting from some perspective. And one of the sort of nice things about this Coulomb branch perspective is there's an obvious big commutative subalgebra, which just comes from the equivariant parameters for your original gauge group G. And so you get functions on the Lie algebra G that are invariant under the group, and a copy of H bar, which you should sort of consider as part of these parameters, because there's also a C star equivariance here. All right, and in SLN, that's the Gelfand-Settlin subalgebra. So thinking about U SLN from this perspective makes it sort of extra compatible with the Gelfand-Settlin subalgebra. And W algebras in type A also have a Gelfand-Settlin subalgebra, where you have to just be a little more careful about the inclusions. And the Cherednik algebra has a sort of analogous commutative subalgebra generated by these guys called Dunkel-Obdam operators. All right, so this is a little bit of a sidebar. I probably shouldn't get too bogged down in this because I don't have a ton of time. But when you have a big commutative subalgebra like this, there's a kind of natural piece of the representation theory to study, which is the modules where S acts locally finitely. For U of SLN, these are called Gelfand-Settlin modules, and I just sort of stole the name and use that in other cases as well. It's very tempting to call them weight modules, but then you get very confused when you think about modules over SLN. So I think it's better not to do that. And over a field of characteristic 0, so I have to add that in now, everything I did before would have worked over any commutative ring, taking that as the base of your KLR algebra, the coefficients of your KLR algebra, and the coefficients of your homology when you computed homology. But now I'm actually going to use the characteristic. The base field of characteristic 0, the category of Gelfand-Settlin modules over this deformed algebra, is equivalent to the category of, well, not quite graded, but graded after taking associated graded modules over the original finite KLR algebra. So taking these Gelfand-Settlin modules undoes the affinization. You're taking a module over this affinized thing, but somehow adding in the C star equivariance that gets you the deformation kind of sends you back to the finite dimensional case. And so somehow if I'm not going to try to do the proof in detail because it can get a little complicated, but the kind of key idea to keep in mind is there's some localization in equivariant homology happening. And so, yes, so as Nidu says, if you sort of look at this C star acting, if it were acting on the loop group, its fixed points would be the finite dimensional group, and there's some generalization of that happening. So it's, because this is all infinite dimensional topology, it's a little hard to wrap your mind around everything that's going on, but that's kind of the key takeaway. Is
that a toy algebraic example?
Gelfand-Settlin modules kind of only sees stuff when you pass to fixed points of that C star rotation, and so you get back into the finite world.
Oh, Ben, is there a toy algebraic
So that's
example?
one way to think about why this characteristic 0 hypothesis is important, because localization just doesn't work the same way in characteristic P.
But is there a toy algebraic example?
We'll get to that, but it just doesn't work in quite the same way. I guess the other comment I will make about this is sort of the key thing in the proof is whenever you have a Gelfand-Settlin module, well, I have this big commutative subalgebra. Michael, were you saying something? Because you're muted.
Yeah, I wanted to ask you for a baby. Is there a baby
Oh, shoot.
Great example when you do or undo this grading. These are kind of the smallest, the first example on the algebraic side with algebras when you can do or undo this grading.
Sorry, you're asking for like a simple example of this theorem?
Yeah, like a baby algebraic example, not topology, just modules over algebras where you kind of.
Okay, so the easiest example is if you take modules over the Weil algebra. So I'm going to take C here, look at things that adjoin X, partial X. So then this S is the subalgebra generated by X, partial X. And hopefully I worked this out correctly. If I take the weight module, the space of weight vectors for -1, so the eigenvectors of -1 under this guy, and the weight vectors for 0 under this guy, then I have maps here. X maps this way, partial maps this way. And then you can check, well, you can keep going with X and partial, but those are going to be isomorphisms at every other step. So this guy is completely controlled. Oops, I did the arrows wrong, but that's okay. This guy is going to be completely controlled by, I did that wrong again, shoot. What happens in these two spaces. And this is, again, the C star sort of fixed point story. And on the KLR side, what's happening is I have one red strand and one black strand. And so I have idempotence where, whoops, I have the black strand on one side, the black strand on the other side. And I have maps between these by pulling the black strand over one way or pulling the black strand over the other way. And these are going to have the same label. So I'm not going to write the label. But the important thing is that going around the loop thus gives me a dot because of the relation when I make a red-black polygon and then I pull it off. And that's going to correspond here to the fact that when I go around a loop, either this way or this way, I end up multiplying by the nilpotent part of X partial. So this dot, this matches up with the nilpotent part of X partial.
Ben, may I ask a quick question?
Yeah.
In your ordinary story, before you put everything on the cylinder, your black previous KLR black lines and your red lines were oriented. Do you assume that they would go, is that correct? Left side and right side of the line, where you would change, say in the case of Grassmannians, you would change either the dimension of the subspace or dimension of the space. That's what the red line does, right? So,
so I would say everything I've done in this talk does not involve strands turning around. So that's sort of I mean, it's an interesting story, but it hasn't shown up anywhere here. So like if we're going to orient things, everything would always be oriented down, and I would never, I haven't taken it out of that world, and I don't intend to anytime today.
So you say that on your cylinder, all the lines are going up.
Up or down, it doesn't matter, but all the same direction.
Which means that if you go around, if you interpret red line as increasing the dimension of the ambient space, for example, by 1, as it was in your first work, then you go, you do
you can't really do that on a cylinder.
Sorry?
I mean, you just can't interpret it that way when it's on a cylinder.
So you don't allow red lines to go around; they're just vertical.
At the moment, they're just vertical. We'll talk about them going around. But I mean, right, the sort of stuff that you're talking about, Lev, always involves kind of like starting over at one end and reading from one end to the other, and like that just doesn't make sense on a cylinder. So,
well, it would if you put one line up and one line down, you would come back to the same dimension.
yeah, well, and I mean, I'll at least get into that a little bit later. But it's, I mean, it's sort of not, I don't know of any kind of natural interpretation like that. Okay, in the interest of time, I won't try to do a more complicated example of this equivalence. Maybe I'll just add a page momentarily. The kind of next most interesting one is if you take this quiver, that corresponds to USL2. And so what this theorem tells me is that the Gelfand-Setlin modules for USL2 correspond to having 2 red lines and 1 black line. And there are sort of 3 interesting idempotents in that case. One where the black line is over at the far end, one where it's in the middle, and one where it's here. And essentially what these correspond to is if you know what one block of the representation theory of U of SL2 looks like when things are integral, you know that there are a bunch of weight spaces that are the same. Then there's a wall where you can start a finite dimensional, and all the weight spaces of the finite dimensional are the same for a while. And then there's another wall where you can start the Verma with a negative weight. And what these idempotents are picking out is what is the dimension of your weight spaces in these 3 regimes. So there are a few examples that you can kind of really do by hand, but it gets complicated fast. All right. And as I was saying here, this proof, the equivalence actually comes by looking at maximal ideals of the Gelfand-Setlin subalgebra, so sort of specifying what scalars these guys act by, and looking at the functor of taking vectors that transform that way in your representation. And it turns out what you'll get is that on these functors themselves, the KLR algebra will act by natural transformations. And there's geometric argument for how to do that in terms of this localization in Borel-Moore homology. In part, that comes out of thinking of these points of the spectrum as co-characters into the normalizer of G in GLV. All right. I think I'm gonna, in the interest of time, I might come back to it. And I'm going to skip sort of the discussion of there's a second way to do this equivalence, which is more algebraic, but if I have time, I'll come back to it later. So why am I interested in this part of the story? I mean, this somehow was actually my first motivation for thinking about things. Well, it sort of helped me achieve something I wanted to do for a long time, which is give a proof of Cauchy duality between category O's attached to Coulomb branches and attached to quiver varieties. So somehow these algebras, these finite algebras, show up both in the Coulomb branch, the representation through the Coulomb branch, the way we just discussed. They show up in a geometric way in the representations of the quantizations of these quiver varieties, and that allows you to prove a Cauchy duality, which I had conjectured a long time ago. Another thing is actually it had not been known before what all the Gelfand-Setlin modules of GLN were, like what the indexing set of simple Gelfand-Setlin modules were. And this actually allows you to construct all of them, but of course only in terms of simple modules over KLR type algebras. So there is some kind of hidden, like, hey, actually computing a basis of this representation would require, knowing all the Cauchy-Lustig polynomials. But it at least tells you how many there are, which hadn't been known before. Similarly, you can do an analogous thing for triadic algebras, which I think was not even a problem that people knew they wanted to study, but which this allows you to solve. And to get back to what Lev was saying about red lines moving around, so just as in the finite case, you don't want to let the red lines cross, in this affine case, before you didn't want to let them move around. They had to stay in one place. But for different choices of this phi, this action on the finite representation, in physics you call this a flavor, for different choices of flavor, which gives you different quantizations of the underlying algebra, so different non-commutative algebras because the relations depend on this phi, you get different bimodules relating them. And of course, in order to get the relations to match up, you have to wrap the red strands around the cylinder, because that will change the factor of h bar that shows up in that red relation, because when the dot slides along, now maybe I actually will go back to that slide. So we have these relations, right? So when a dot slides all the way around the cylinder, it picks up an h bar. And on the other hand, what happens when I get rid of a red-black bigone depends on that C star action. So if I send my red strand around the cylinder, I have to change the algebra that's acting at the top. All right, so we get a bimodule that relates different quantizations. This is what we sometimes call twisting bimodule. And derived tensor product with this guy gives what we call twisting functors. And these are constructed in general for all symplectic resolutions. So this is just a special case of a general construction. And you can prove that these give you braid group action. This is actually also a general result due to myself, Tom Braden, Tony Licata, and Nick Proudfoot. And you can even upgrade this to an action of tangles on the category of Gelfand-Zetlin modules over this algebra. That action of tangles, of course, gives you a link homology. And because we can relate things back to these KLR algebras, this recovers my old work on categorified Rashidi triad. And so in particular, this sort of geometrically constructed, I mean, maybe it looks algebraic, but it's using sort of general things about symplectic resolutions, recovers these categorified not invariants I'd constructed before. In particular, we now know in type A, those match on a resonance. And I'll just say, this seems to match up with some predictions of Witten's from his paper on knots and five branes, that you could construct a knot homology with A branes. So I interpret that as modules over a quantization, using this canonical coisotropic brane over a space of Hecke modifications, which is actually an example of a Coulomb branch. All right, are there any questions? So, this theory I did before, which was kind of purely combinatorial, purely just like, hey, look at these diagrams, check some relations about them. Oh, look, things satisfy not invariants, actually sort of comes geometrically out of the story. And there's a Cauchy dual way of doing this, also using quiver varieties. So that sort of Cauchy duality tells you you really have two constructions of these non-homologies. All right, so let me now talk about, sort of start getting back toward those non-commutative symplectic resolutions. So this next part, there's a couple of different ways you could sort of say what I'm trying to change. You might just like characteristic P and say, hey, wait, your theorem there had a characteristic zero hypothesis. What happens if instead you put something of characteristic P? But that's probably a relatively small slice of people here. Maybe more people would say, oh, wait, I wanted to know about those non-commutative resolutions. I wanted to know about coherent sheaves on a resolution of spec A. Or you might have gone to, for example, this talk of Aganagic in the Western Hemisphere Colloquium on Geometry and Physics in, I think it was June, or read her recent paper on this and said, wait, what is all this stuff about cigars? What is going on here? And interestingly, whichever kind of person you are, you should actually do the same thing. And Nitu had asked, does Havana-Rosansky mean triply graded? No, I mean SLN homology. So this all depends on some quiver, and that underlying quiver should be an SLN quiver. And in theory, the triply graded homology should be there as some kind of large limit, but I don't really know how to explain that limiting behavior, certainly not in these terms. All right. So let me first say a tiny bit about characteristic P, and those of you who don't like characteristic P can just be patient for a couple of slides. So I can try to do exactly the same stuff over characteristic P and look at, well, I could say Gelfand-Zetlin modules, but actually my algebra is finite dimensional over its center. So, you know, irreducible modules are automatically finite dimensional. So somehow that isn't as much of a restriction anymore. But I can try to understand all finite dimensional modules by diagonalizing this commutative subalgebra S. And I do have a real restriction, which is I'm going to want those to have sort of an appropriate integrality property. So there's something really different that happens in characteristic P, which is if I wrap a strand around the cylinder P times, the shift becomes trivial. So, right, I had this relation before of my dot goes around and I add H bar. And in characteristic 0, well, I keep going around more and more times and I add more and more copies of H bar, and I always know exactly how many times I went around because I'm never coming back to the same shift. But in characteristic P, I go around P times and it looks like I just came back to where I was. So taking that observation, generalizing quite a bit, what you can find is if you look suitably generically, the category of finite dimensional modules over A1, so this is the deformed algebra with quote unquote integral weights, is actually equivalent to the category of modules over this algebra R. And I put 0 here just to remind you it's not the deformation. It's this original algebra I wrote down where nothing happens to dots when they go around the cylinder. But it's sans serif, so it's the affine version of the KLR algebra. So there's sort of a strange thing that happens, right? I take this algebra, I take its finite dimensional modules with integral weights, and I get representations of a very similar looking algebra, which I know is actually a resolution of the original A0. So this is another one of these manifestations of when you deform, that's the same as resolving. So this is sort of I think a pretty interesting fact on its own, but it's actually kind of motivating me to look at other things. And there's a geometric proof, which is sort of you use the same localization, but since you're doing things in characteristic P, you can only localize to the fixed points of the P torsion in your C star, not to the fixed points of the whole thing. And if you sort of think about what that tells you, that's exactly telling you about this R0. And I didn't explain the algebraic proof the previous time, so if I try to explain both of them, I'll have to do them together. All right, so why does this have anything to do with coherent sheaves? Well, there's some fancy characteristic P stuff going on, which I think just confuses people if you try to explain it. But kind of the key underlying thing is this Coulomb branch has a quantum Frobenius map. If you look at the quantum version of it in characteristic P, then the non-deformed algebra maps into the center by a quantization of the Frobenius map. And there's a way of sort of localizing this to a map of sheaves from the structure sheaf on some resolution to some funny version of a quantization of that resolution. You have to do something a little strange here. Right? You're taking a deformation of the structure sheaf. That's not a coherent sheaf anymore, but you somehow restrict to this, somehow it's pushed forward by Frobenius is a coherent sheaf. Okay, well, that's a little strange, but you know, you go read Bezrikov and Kalin's papers and they tell you how to do this. And then they go through a somewhat complicated construction, which kind of morally for us is taking this commutative subalgebra and trying to diagonalize its action. And you might say, wait a second, that doesn't make any sense. You're not going to have the right kind of local finiteness to diagonalize it. And I say, yes, that's why you have to go through this whole crazy business of an ATOL cover, but don't worry about it. It'll all work out. And so out of this whole business, one ends up constructing a special vector bundle, which I'll call T. And well, I was doing everything in characteristic P, but actually there's a sort of canonical way to lift this guy up to characteristic 0. So well, the past couple of slides involve this scary characteristic P stuff. You know, after kind of digging through the garbage pile of characteristic P, I can pull out something in characteristic 0, which is interesting. And in fact, it's something that has this very nice property. It's a tilting generator. So it's a vector bundle. It has trivial higher x with itself, and it generates the derived category of coherent sheaves. And whenever I have these properties, then I have an equivalence of categories from dB of and T modules to dB of n tilde, given by taking x with T. All right. Well, under some restricted but not terrible hypotheses, this vector bundle T is a tilting generator for my resolution. And its endomorphisms are exactly this affinized version of the KLR algebra. And so the fact that R is a non-commutative resolution is actually corollary of this, that because it has the same category as a commutative resolution, that tells you it's a non-commutative resolution. All right, so maybe I'll pause to see if people have any questions here.
I'm a little bit lost, but let me ask you just a question. The statement that you made on top of this page, would it be would one example be that coherent sheaves over Hilbert scheme is the same as modules over the endomorphisms of Procesi bundle?
Yes. Yes, the Procesi bundle is one example of
that's your
a tilting generator.
Okay.
And in fact comes out of this construction. So that's sort of one special case of doing this, and which had already been known from this work of Braverman-Finkelberg and Ginsburg.
So from our perspective, a bunch of unknowns gives you this tilting bundle. Okay, thank you.
Yeah, I mean, one thing which I would really, really love to understand is how does doing this story for the Hilbert scheme tell you anything about this non-homology story? I honestly don't know. That's something I would really, really, really like to understand better. All right, so let me just, I had mentioned at the beginning that I kind of wanted to relate this work of Wagenknecht, so let me say some tiny amount about that. So, you know, we now know there are actually several different non-commutative resolutions of these varieties. They come from different orderings on the red strands, right? So this, I didn't sort of make clear all the dependencies here. This guy, R, this actually depends on the order of the red strands, which in the terms I've been discussing before means it depends on this choice of flavor phi. You guys not see that? That's interesting. Did you just see me change slides or not?
No.
Oh, that's interesting. Shoot. Well, let me try sharing again, because I wasn't. Okay. All right, just it's not going to be good if you guys aren't. Okay, good. Okay, so you might ask, yeah, it depends on the order of the red strands. So how are these guys with different orders of red strands related? I mean, in fact, it's general theorem that all of the resolutions, commutative, non-commutative, they all have the same derived category attached to them. But that equivalence is not unique. There isn't a canonical way of matching the derived categories. There are interesting auto-equivalences that come up from constructing different matchings between them. And when you combine these together, through older work we knew, again, sort of general stuff about symplectic resolutions tells you you're supposed to get an affine braid group action here. And this is the characteristic P version of twisting functors. And it turns out that when you sort of translate these over into the combinatorics, what you get is cylindrical versions of these R matrix bimodules. So you get pictures like two red strands crossing, and then your black strands doing whatever around them. And the reason it's going to be affine is I can also cross around the back. I also have a crossing like this. Sorry, just. So I can also do this, and that gives me kind of the extra affine generator, the S0 of the affine braid group. So now I have my original sort of finite braid group, but I've upgraded everything to be cylindrical, so I get an extra interesting action. All right, and this had shown up way before in work of Bezrukhovnikov and Akunkov, all these people, and also shows up in this talk of Nina Aganadich I had mentioned. All right, so it turns out that you can extend this to an action of affine tangles. And I have to admit this part isn't really written up yet, but I mean, it's essentially all the local moves are already proven in my old paper. So somehow it shouldn't actually be very hard. But you have to come up with affine versions of these cup and cap bimodules. And an affine in type A, you can even get affine foams if you want to. And essentially all of this stuff is we already have in the finite dimensional case, the kind of in a plane instead of on a cylinder case of all of these actions. And it's always defined by some, sticking in one interesting local vertex, and you just do that on the cylinder instead of in the plane. All right, well, you can also interpret this as giving you a link homology constructed out of these coherent sheaves. And basically, because all you're doing is taking the finite construction and sticking it in a cylinder, that's not going to change the knot homology. So this affine tangle action gives you a knot homology from coherent sheaves. The characteristic zero construction we discussed before gives you a knot homology from quantum coherent sheaves. These guys are equal because essentially one is just kind of taking the first one is kind of taking the second one and sticking it in a cylinder. We already talked about how this guy constructed from quantum coherent sheaves matches basically on the nose with my old work. That was purely algebraic. And then there's this recent work of Nina describing things in terms of physics, but she's working with the same category of coherent sheaves. And so one just has to kind of go in and look at what Nina's doing and sort of say, oh, okay, these objects that she's constructing, and she herself says things aren't kind of totally rigorous, but she gives you this kind of guide to find the objects you want. And in fact, the ones I'm using here are exactly the ones she's telling us to look at. In particular, she sort of says that the braid group action she wants is this Bezrukhovnikov-Akunkov one, which is the same as the one that comes up here. Whoops, here. And then, actually, to me, the more interesting part is how to get the cups and caps, and she has this kind of slightly implicit description of them in terms of, you know, what happens with you know, central charges and stability conditions as sort of certain things go to zero, and that in our terms you can actually like directly interpret by looking at these red lines and like having them collide to make a cup and a cap. All right. So I think that's everything I wanted to say. Sorry if I should have stopped at 50 minutes after, but at least I didn't go for the full hour. So thanks, everybody.
Let's thank Ben. Questions?
As I was coming up to the end, I was like, oh, I'm even ending a little bit early. And then I was like, oh, wait, no, it was supposed to be a 50-minute talk. Shoot. Let's see, you said phones show up in this picture. Can you provide any insight? So, you know, there's work of Marco Mackay and myself that describes how foams act on the finite versions of these categories, basically by some kind of natural bimodules where you have red strands, instead of like just crossing, like they actually kind of collide. And you have to kind of carefully define what the vertex sitting at that point is, but it's something pretty natural, something that comes up if you just carefully study the case where you have two red lines and say, oh, you know, what's the module in here that corresponds to the correct, you know, highest weight for this weight you want, that'll guide you to the right trivalent vertex to give you foams. And so I think, again, you can just kind of take that trivalent vertex and insert it into the cylindrical picture. I admit there's sort of a lot of these points here that I've not written up because it's like, oh, well, I mean, obviously it must work to just stick this into the cylinder, but then how do you actually carefully write up that happens? I think that's all I can say. I don't know if you have more question or should just pass to someone else.
Ben, I was curious if this trivalent vertex had anything to do with reducing your SLN to a smaller n, or what is the combinatorial meaning of these vertices?
So the trivalent vertex, what is the combinatorial meaning? So, you know, what you need to have to get foams, right, is you need to have a vertex that's like, here is the kth wedge power, here is the lth wedge power, and here is the k plus first wedge power, right? And what always ends up happening is, well, if you look at the algebra categorifying this tensor product, inside here, there's a unique simple, which is highest weight with the correct highest weight for k plus l. And so then if you kind of think about what the basis and relations of that simple is, it kind of leads you to the right trivalent vertex. And the thing that sort of, I mean, it's completely forced on you by the combinatorics, but it always looks kind of weird, is you have to have a bunch of black strands exploding out of here to make all the weights match up, right? I mean, basically, you know, sort of this guy involves, here's some box, here's the red strands, and then there's some black strands that come out that sort of make sure you're in the correct weight space. And you have to basically take this box and crunch it down to this trivalent vertex here. So kind of the easiest example is in SL2. Well, I'm not even going to draw the one with highest weight 2 because that's boring, that's the trivial. But here you have 1, 1, and then you have to have a black strand kind of popping out of there to make sure you have weight 0 rather than weight 2. And it just gets weirder as you get higher up. It's sort of not too bad, but it sort of starts looking kind of complicated.
Thanks.
And yeah, I guess in even in higher rank cases, you still have this guy of 2 and then 1s and then a 1 popping out. But you can have other situations like here's 1 k minus 1, and then popping out you have 1, 2, etc., all the way up to k minus 1 to get the weight right. It just gets more complicated from there.
I'm sorry, Ben, may I ask you a basic question? Maybe you said first talk. I just realized that I'm totally confused. So when consider SO2 case, Commutative stuff. So they're using Nil-Heke algebra. As you told me, Nil-Heke is GLN equivariant homology over flag variety plus cross flag variety. So again, this is the algebra